So my friends, I cannot wait to hear what you have to say about these figures that I asked you to look at. And I'm curious. So hopefully you have read those 2 pages that I asked you to read. And you know what a Mobius geometry is. What is Mobius geometry? Can someone tell us? Nathan.
We have this the C plus and M, where M is the Mobius transformation.
Nice, there's our space, and then just Mobius transformations of them. Basically called the last like gajillion weeks in this class, right? Where we've been before. So it's just the extended complex plane. We got good old infinity in there. That's actually really important for this problem. And in fact, for me to think about this problem, I really had to think about the Riemann sphere to make sense of this. And then that is, I'm going to make it dotted because that 0 is behind that sphere. It's hard to see it. Let's say here's like the unit circle right here. And 0 is just a point down there. Cool. So what does it mean to be congruent? For 2 figures to be congruent in the Mobius geometry. Christian, what does that mean?
It means there's a Mobius transformation that takes one figure to another figure.
Yeah, exactly. So did anyone work on this? Just like, let me just be. Does anybody have any ideas about this one? You got some ideas? You got some ideas?
I have a question.
Oh, questions, good.
Yeah, like one of the thing said that any 2 clients are congruent in Mobius transformation.
Yeah.
So does that mean they're all congruent?
Well, it means that any particular 2 clines, so like that, and that's not a cline.
So yeah.
That and that, or any of these, now these are separate. So I can take that and turn it into that, I can turn that into that. These are all congruent things, they're all the same.
Okay.
But the minute they start touching, things change, because that's no longer a cline, right? These are unions of clines. So Lou, you said you had some ideas. Tara, did you say you had some ideas too? Okay.
I don't think so.
That's cool. What were you thinking?
So I was looking at it and I was kind of thinking to myself, like, how many points do they share? So like I looked at A.
That's a good start.
Yeah. And right, so so 2 of the clines are touching one of them, right? So like the top and bottom ones are touching the middle
Can you
one.
use the letters I put up there?
Yeah, A has the 2 like circles that are touching the middle circle. So I was then looking for other ones where 2 of them aren't touching, but they're touching the same kind of like intermediary. So like F, I would say, is congruent.
So let's see. Yeah. What did we do to this middle one?
We
Essentially,
essentially kind of like unfurled it.
Oh God. Oh, I love that word. That's so beautiful. Yeah, we just mapped one of these points to infinity. Right? So take a point out of here, take this point, shoot that to infinity, that breaks this apart, it becomes a line. And as Lou said, if you unfurl it, so think about, here, let's unfurl it just a little, break it apart, and then we've got that guy and that bigger one, like that. And then just keep stretching them out. Send these 2 points to infinity, and it turns right in, and I got it aspect, it's upside down. And then, do it the other way. Break it apart in a different way. But yeah, this A and F are congruent, definitely. I'm gonna mark off things as we. What else?
Yeah, and then I kept looking at it and then I saw H, and it kind of looks, following the kind of unfurling idea, you just kept going until you turned the circle back inside out and put the 2 outside ones inside of it.
Absolutely. Or just an inversion on this guy, right? So we could invert both these circles on this circle, and then this one would go inside and that one would go inside. So I agree that H is also, let me cross out the letters instead of the whole figure and add extra lines. Are there any others that are like that in that we're getting as an equivalence class of critters? Yeah, go ahead.
Well, I also, in like a separate group, I thought that C and G would be congruent, because I lied, it was B and G.
Okay, I was gonna say,
yeah, because
yeah.
the two lines, while it looks like they're only intersecting at one point, they're also intersecting at infinity. So they share 2 points, and then the circle and the line that's vertical are also sharing 2
Okay, so
points.
let's slow down.
Okay.
Slow down. That's good.
Okay.
That's good. So, do we see this? Do we see that B and G can be mapped into each other? We've got to take infinity into account. If you don't think about the Riemann sphere, this is really hard to picture. So let's actually look at that one right there. So if I drew B, the straight vertical line is a circle, a great circle. Let's get rid of that unit. That's not helping, that unit circle I put on there. But that straight line is just a big circle that goes through infinity. And then the thing that looks like a circle is just a circle. And then the other one is a circle that is orthogonal to that first one. So it's another longitudinal line. 2 longitudinal lines in a little circle get us figure B. So, and then I just want to point out another thing, that a clue that I used was that angles are preserved by Mobius transformations. So if you intersect at 90 degrees and you get changed to something, the intersection doesn't get changed in the angles. So here I have 1, 2, 3 90-degree angles. So if I can find that somewhere else, that's the same thing. So,
The fourth one is hidden. Like in B.
oh, is it?
Yeah.
Oh, yes, thank you. That's right. It's at the top. Yeah, it's right at the top. So then there's the fourth one out at infinity. It's this guy right here. Thank you. Good. So then there's 1, 2, 3, 4 there as well. Yeah, nice. So, okay, so let me get back. So B is equivalent to G, and then what were you going to say with that, Liz?
I think that takes it for those ones.
I
And
do
then
too.
Just to finish it off, I think that the last 3 are all congruent to each other as well.
Cool. Yeah. I don't know about that. Let's see. So hold on. So I can't remember what I did. Let me look at my work from last night. So I had A was equivalent to H was equivalent to F. I also had D in the class with A. So I had this guy in there because those circles come up and they are all, wait, is that right? Wait, what did I just say? That this was equivalent to that?
The 2 lines are sharing infinity.
Yeah, these two share infinity. Let's see if we can draw it in the sphere really quick. So let's see. So yeah, it definitely helps to have this picture here. So we've got this guy, which maybe we'll just say is this. Comes around that way. And then this other one is parallel to it. So parallel is really hard to see, but think about lines of longitude, how they look parallel in the center, and then I think they probably intersect. And yeah, no, that looks like garbage. That's a lie. Where's the back button? I think these are just 2 circles that go through infinity, but they're just tangent at infinity. So you got like one like that, and then another one kind of like that, kind of like off at an angle. And then they're both tangent at infinity. And then that guy is just tangent to one of the 2. So he's kind of just sitting there. So yeah, so that is this figure here. So you see that? You see that? Here's a little snowman head. Here's snowman. So snowman head down here, and snowman body got stretched to infinity, and then snowman legs is this other one here. So I think B is in that class. What are you thinking, Kendra?
So would that mean that E is in the same class?
So E, I think these are all three simultaneously tangent. So what did I put E in? I thought E was equivalent to C.
I see.
See, because they intersected 0 degrees,
Mm-hmm.
0 degrees, and then
They all.
they all intersect. Wait, but
No, I'm understanding what you're saying because in your diagram,
yeah,
you'd make another circle.
yes,
So that means that the infinity is the one intersection point,
yeah,
and then you'd have the center line, and then 2 circles on either side.
yeah. So I think this makes sense to be that. Because this is just circle that's got infinity on it. But now I'm really wondering, because there's 2 distinct points of intersection. That's snowman. Oh, that's snowman. We already know that. What am I thinking? That's snowman. It's A. Yeah, I gotta stop thinking about H. That's snowman. So this one here is this, and then I think that's that D as well.
Mm-hmm.
It's just that here the tangency is where we can see it, but here, no, because these three, they don't, so this one is equivalent to, let's say there's infinity, just wrap that up, and then this guy's like right here.
So that's A.
That's snowman, yeah.
And so then it's E and C.
E and C, yes. Yeah, and these are just, yes, E and C. E, because this can be turned into that thing there. They're just also, there's infinity. It's actually easier without the damn sphere. They're just all like that. Yeah. Anyway. Fun stuff. Do you agree with this?
Yeah.
Okay, cool. I didn't know if I contradicted something you were saying. No. That's exhilarating.
So B, I got a little bit lost.
That's cool. Yeah, fair enough.
B and G are congruent to each other, and then all of the other ones are in their own group.
Yeah, so B and G, and then E and C. And then everything else is in this snowman group.
Is D with the snowman group?
And D is in the snowman group because Ella, D could be thought of like this, where they're touching up at infinity. These two things, they are tangent at infinity.
Okay.
And then this guy's sitting there. So imagine wrapping this up like that, and then this up like that.
Okay.
Yeah? That's crazy shit. That's just really, really fun. So I hope you had a lot of fun with that, or you were doing something fun in its stead. Any other comments, questions on this? There you go. Yeah. All right. Homework was just up here. It's also in the calendar. So if you look at the calendar, you'll see 4 problems. I think I've got them for next Friday. So we set these ideal dates and then we see how things are going. Yeah, I think this is quite doable. It would be, as always, it would be great if we could discuss these on Monday. Wednesday's not as great. So I'm kind of excited about today. I feel a lot of pressure because everything comes together today. Like almost everything's coming together in the next 2 classes. You've been busting your ass. Think back to all the very early days about reflections. Translations are 2 reflections. Rotations are 2 reflections. Rotations, did I say that? So what did I say? Translations, rotations, dilations are 2 inversions around different circles, concentric circles. All that stuff is happening today in a way that puts it all together. So let's just start. Let me just get to my T here. We are going to talk today about hyperbolic geometry. Please read this section. Start reading it. So that if I miss little tiny details, you will catch them. Okay, so this is actually very closely related to the Mobius geometry. It's a special version of it. Like I drew that stupid umbrella. I was looking at that lecture, that horribly drawn umbrella. That's the big geometry, the Mobius. This is a specialty of that. And here our space is going to be this thing called D, which is just the open unit disk. So D, we're going to think of as the unit circle centered at the origin. So right there is 1, there's I, there's minus 1, there's minus I. It does not include the boundary. In some ways, what we're kind of thinking is the whole plane will be shrunk into there, but in other ways, we're not thinking that. And this is where things become a little challenging. So D is this open thing here. D equals the set of all Z such that Z is less than 1 in magnitude. Just that thing right there. It's all the stuff in between. That's where everything happens. All of our geometry happens in that circle. Around the boundary, we have a closed circle. So the boundary is this circle of radius 1. We denote it as S sub infinity 1. This is the circle at infinity. It's going to take the place of infinity for us. I'll tell you something in just a second, but this is the set of all Z such that Z is identical to 1. Okay, Christian? Yeah, all right, cool. We will get, I hope we get there. But when you are traveling in the hyperbolic plane, distance starts to become, it gets harder and harder to get to the edge. So for example, traveling this distance here might be a mile. Traveling this same distance here is 1,000 miles. And then that's 10,000, and then that's a billion, and then that's a trillion. And the closer you get to the edge, the more scrunched up things get. So if you were living in there, and actually, if you have access to Steam, the PC gaming thing, there's a game called Rogue on there that literally takes place in the hyperbolic plane. It's an RPG, overhead view. You move around in the hyperbolic plane. This summer, I might check it out. I was like trying to convince myself I needed to play it to get ready for class over the break, but I was like, no, just work the damn problems in the book. But I would check that out. I would also check out any of the works of M.C. Escher. I guess not all of them. If you look up M.C. Escher, and you look up hyperbolic, you'll see that he did an incredible amount of work in tiling the hyperbolic plane. In fact, let's just bring it up so we have this idea in our head of what this thing looks like in a way. And you'll see what I mean about the distances. I think this is worth looking at. Other users, yeah, that's me. Let's see, power on here. Is that thing rolling there, Vivian, or is it? Yay! And Actually, this was one of the first things I put up in our class page over the break. Well, let's just take a look really quick. Okay, so Escher did a lot of stuff. He also designed what's the building at the end of campus? Claver. He also designed Claver. And what I mean by that is
It's not real.
yes. This is the building he designed right there. That is Claver Hall in my mind. Oh well, hey.
Well, yeah.
You can't see anything. What an anti-dramatic moment. Now I totally screwed us. Is it coming back? Thank God.
Yeah. You just need to change the output.
Yeah, I think it's on HDMI.
Oh. That's Claver Hall in my mind. That's what it feels like anytime I try to get to the second floor and I have to go down. Okay, so this is his work in the hyperbolic plane. There's a nice color piece right there. And those are both tilings of the hyperbolic plane. Can everybody see that okay there? Yeah, so he really worked in this, but imagine these fish are all the same size. It just looks like they're getting smaller. So you can see that there's just this infinite regression toward the boundary. And it never gets there. Never gets to the circle at infinity. Let's look at a couple others. He's got, I'd like to get a high res one. Let's go back here. Let's see, tools, Escher, hyperbolic, tools. Give me the good ones. This used to have an option for quality under tools. Apparently, quality is not a problem anymore. So, ooh, this is a good one. Look at that. Oh yeah, I want to show you this because how did Escher do it? Do something. Give me one. I like this heaven and hell one. This is one of my favorites. Why can I just get a big picture that is like more than 30 by 30 pixels? Can I do that, Google? Oh my God, you're selling me shit. Unbelievable. Okay, can I please now? Ah! And I think they tweaked this because people were just taking images from things. That's 900 by 900. That's almost 3 by 3 pixels. Oh, you're meant to confound me. Anyway, I really like that one. Just the interplay of the opposing angels and demons. It's really beautiful. He did a lot of really cool stuff. I just saw another one in here that I kind of want to see. This one here, it's not a hyperbolic thing at all. But do people still like, when I was in college, people had these Escher prints up on their walls. Oh, vile, vilest of vile things. There we go. Come on. And then we're, okay, whatever, Guardian. But anyway, you can see he did a lot of really cool work. When I was in college, this and Salvador Dali paintings were like in every dorm room. Are the Dali paintings still up in the dorms? Like, you know, what are people
There's
putting
one
in?
in the student center.
In the student center?
Or they used to be at, I was just like,
Yeah.
like weed.
How do I make what? Like pictures of weed? Is that what you're saying? Like posters of,
yeah.
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 We are talking about what I'm thinking, right?
Yeah, like what do they have now these
In the
days?
dorm.
In the
Oh,
dorms.
germs. Like
Yeah.
if they had people have pictures of marijuana plants.
Yeah, so.
Cool, I have those in my.
Bless you.
Thank you. Issues of high times sitting around. Okay. Anyway. Good. More content on film. Will go well for my next review. So. Anyway. Escher did a lot of work with this plane. He's probably the first person to make it really famous. This model, it's only one of several models. It's called the Poincaré model. Oh God, did I umlaut that right? No, there's no umlauts. He's a French dude. Poincaré model. Poincaré disk model, probably even, of the hyperbolic plane. There are funkier ones. The Klein model is a very strange one. If we get time to look at it and we start thinking about the geometry of the universe, we're gonna be there. We'll get to see it. So this thing here, this hyperbolic plane actually has a lot of applications. I was talking to Lou about it a little earlier ago. In data science, if you do machine learning, this is actually recently, like this is a hot topic of research, using the hyperbolic plane to store neural networks and to measure the size of neural networks. I think also in, now it's escaping me now. But there's actual applications for this that are beyond just having fun with it in geometry. So, that's our space. I haven't even got to the transformations yet. So our transformation group is going to be called H. And it is the set of all Mobius transforms T such that T maps the disk, this disk D, back onto itself. I put equals there because it hits everything. It literally just takes it, and for every point here, you can hit it with that T, and the output of that T, if the input is in the disk, is still in the disk. So let's just write what that means there. T maps the disk back, and I'm going to use a fancy math word, onto itself. And that means it hits everything. It's surjective, if you've had that word in your life. And we might have heard it in here a long time back. So, hyperbolic geometry is this pair. Our space, D, along with this transform group, H. And now it gets heavy. This is the easy part. That was the easy part for me. Now I have to start talking about some stuff. So, I'm gonna jump ahead. In my notes, I jumped ahead. Everything in here looks like this. Every T in H has the form. So that you'll at least know kind of what these look like. It's not just an arbitrary Mobius transform. It's T of Z equals e to the I theta. So a rotational number out in front, magnitude 1. Z minus Z naught over 1 minus Z naught conjugate Z. And that's it. So it's a Mobius transform. You've got Z minus some number on top, and then 1 minus the conjugate of that same number times Z on the bottom. And this is for some theta that's a real number, and Z naught that is in the disk. And notice that T of Z naught is 0. All right, here we go.
Wait, is Is the circle at infinity included in the space?
No. It will be included in our thinking a lot, but it is not in the space.
Right.
Yeah, exactly. I'm glad you asked. That is an important distinction. But we're going to use it like crazy. So, and the weird thing is we'll actually be using the points outside of the space that we're in all the time. I don't know what, I guess they're all just like ghosts of infinity or something. Oh, there she is. That's right, you told me. I think you told me you were going to be late.
Yes.
Yeah. So, our main tool will be inversions. And a very specific type of inversion. We're going to take, so here's S1 infinity. So there's the infinity goes in the bottom, which I really find weird. Got 0 in the center. Right on the edge, actually on that circle is the number 1 in the plane. And what we're going to do is we're going to take clines that intersect this thing orthogonally. So try to draw your best circle that intersects that thing orthogonally. And you can maybe put a little right angle there. Our main tool is going to be inversions around such clines. And let's talk about that a little bit. It's probably going to be a little rough catching up just a bit, Grace, but yeah, okay. So we'll be inversions about clines that are orthogonal to the circle at infinity. And let's talk about what that's going to be like and just get a few things out of the way. What is the, and I want to see if you kind of remember that. If I invert C about S1 infinity, excuse me, if I invert S1 infinity about C, so I take this as the thing I'm inverting around, what do I get? So imagine you're inverting around this guy. What happens to this?
The same thing.
Yeah, nice. Yeah, why is that? You're right.
Because like the inside is just like moved to the outside, and the outside's moved to the inside.
It is, and it's because of the orthogonality as well. Yeah. So the fact that these two clines are orthogonal mean that if I invert this one around this one, and vice versa, if I invert C around this, they don't change. So things are getting clearly heavy. But we've seen this before. We did a lot. This is why we did all this work with inversions. Because inversion about an orthogonal cline inversion of cline A about an orthogonal cline maps A onto itself. So if I invert this C, if I invert this disk D, or the circle C around this guy, I just get that guy back. And also if I invert C around the unit circle, I get back C in the same way. So there's kind of this symmetry there. Also, the inside is preserved. So when I flip this C over this circle, when I invert it over this, the inside stays on the inside. And when I invert this circle over this C, the inside stays on the inside. It's almost like they're hinged right where they intersect, and they're just kind of flipping. with a little bit of scaling, right? So it's kind of like you flip it, and then this whole part turns into that, and this inside part turns into that outside part. And let's put a note here. And the interiors of the clines are preserved. Make sure. Okay. Yeah, I think I got to what I wanted to say there. Every T in this transformation group is the composition of two of these together. So let me put that in the middle here. Every T in our transformation group H is the composition of two inversions about clines that are orthogonal to S1 infinity. Yeah. Seems like the infinity should be on top. I had to scold myself about that many times while preparing today. This isn't shocking because every Mobius transformation is an even number of inversions. Some folks use that on the last assignment. But here it's very specific ones. We can only invert around clines that are orthogonal to this guy right here. Think about that Escher image we looked at the beginning. Think about how it was tiled. It was tiled with things that looked like this. They were all these clines that were orthogonal to the outer disk. I can pull that back up, but you should really go look at some Escher work on your own. And it was just various clines. Notice that straight line through the center is also a cline. It just includes the infinity at the top of the Riemann sphere. So these are clines too. These are the only straight looking lines that we'll see. So these two things here, we have straight line, basically I have two straight line clines. This, oh my God, I did not hit the center. I meant through the center. So in other words, here, let's do it again. There's S1, there's the unit disk, the one that goes right through 0, and the one that goes right through 0. I guess actually, any of these, sorry, that's a lie. Straight line clines are included. So we have infinitely many of those. They're just the spokes on the wheel, and they include infinity. So we're going to invert around things that look like this and things that look like this, and that's all we can do. And we're going to do it twice. So everything in that group can be accomplished by maybe flipping over something like this, and then something like this, or something like this, and then something like this. All our actions are going to happen in that way. Let's get into it. And the way to really see this is to prove this theorem together. So by proving this theorem, I kind of got a handle on what this is all about, and I think we're right at the precipice of jumping into a big pool of stuff we've learned. It's all right on the other side of this gate right here. So watch for all your friends from this semester. Cross product might show up at some point. Keep an eye out. So here's the theorem we're gonna prove this. We don't often prove things in here, but we have to prove this together. Theorem 513. Any Mobius transformation in our group of transforms H is the composition of two hyperbolic reflections. And the hyperbolic reflections are the ones I just described. Let's put a little note here so that we remember what that is, i.e. reflections about clines that are orthogonal to the unit circle. So I've said that, I've hinted at it, let's prove that we can do it. So what I'm going to do is create a hyperbolic transform. So I'll write kind of the goal here so you know what's coming up and you'll see it as it unfolds. So this is like the plan. Create a T in H such that T of Z naught equals 0. T of the reflection, the symmetric point relative to Z naught, goes to infinity, and then T of some other point goes to 1. Does that look familiar? That's the cross product, right? So we're literally going to build that cross product formula that does this with just flipping things over. And so some geometry is involved, and it's really beautiful, and you're absolutely going to understand this, I swear to you. And we're going to go slow so that you do. Let's make a little note here. Z naught equals the inversion of Z naught star is the inversion of this in that unit disk, unit circle. And we might want to add here for some Z naught and Z1. All right, picture time. So let's take, this is the proof, take a T from H. By definition, T maps the disk back onto itself. By definition of being in this group. We only have things that do that, so we know that's true. So, let's take a look here. So here's D. We don't have the edge. And then here's D again, over here. And here's 0 right in the center. So if T takes this thing and sends it back here, 1 to 1 and on to, then there's something over here that hits 0. Something has to hit 0 because otherwise, if it doesn't, we haven't hit the whole disk. And that something has to come from the disk. Let me stop. Let you get caught up. Think about what's going on. Super mindful. And then the geometry is going to start. So let me know, take a minute, make sure you understand what's set up. And Grace, that D is just the open unit disk, centered at 0. It's just this guy right here. And that H is the group of all Mobius transforms that send this back to itself. That's all. So that's kind of all you missed. Can I go on? Let me know. Yeah, I'm seeing some nods. Because this T sends all of these points to all of these points, one of them gets sent to 0, and that starts the construction. Okay. So now, I'm going to take the inversion of this z naught. So here's 0, right here, right in the center. The inversion of z naught is on a line through the center. I'm going to flip this. I'm going to reflect this z naught over this unit circle. So I know it's on a line through the center, and it's on this line somewhere. So let's say it's out here. Z naught star. So Z naught star, I wrote it over there, but I'll write it again, is the inversion of Z naught over the unit circle, which we just have fancy note. That looks so damn fancy. That's just the unit circle. But we're getting highfalutin. All right. Cool, cool, cool. So, Z naught and Z naught star are symmetric. Let's just make some notes here. Note. Z naught and Z naught star are symmetric with respect to the unit circle. I'm going to write it here. I'm going to write unit circle instead of that crazy notation. What do we know about how Mobius transformations act with symmetric points? What do they do with symmetric points?
Maintain symmetry.
They maintain, they preserve it. They preserve symmetry. So if you take a pair of symmetric points with respect to a curve, and then you run this t. So you take this t, it's a Mobius transformation. You take these 2 points and this curve, the output will produce, we know it'll produce this, actually it'll produce the same curve. It produces the circle, but it also sends these 2 to symmetric points. So if Z naught goes to 0, and Z star naught is symmetric, what is symmetric to 0 in the complex, extended complex plane?
Infinity.
Infinity. So Z naught star gets sent to infinity. So let's write that up. So since Mobius transforms preserve symmetry, and Z naught and Z naught star are symmetric, and 0 and infinity are symmetric, if Z naught goes to 0, Z naught star has to go to infinity. Take a moment to sip on that. While I sip on this, and erase the left side for more. We're almost done. We actually have we actually have 2 of the things we wanted. Got them right here. Now, what we need to show, where's that damn circle argument? Okay. Hold on. I got this circle argument. Why is it? Oh. Yeah. Okay, cool. So what is the inversion? What is the inversion that does this? That's what I'm going to show you now. I'm going to create the circle that if I invert Z naught about it, it gets sent to 0. So we need to map this action T sends Z naught to 0 and Z naught's symmetric point, its reflection, to infinity, to a reflection in a cline. Because the whole point of this theorem is that the Mobius transformations we're talking about are actually just 2 reflections over clines. So we're going to produce those clines, and we're going to use geometry to do this. So let's get this disk back. Let's just draw the damn border. And here's 0. And I'm going to put it on this side over here. Let's just say there's Z naught. And then there is Z naught star out here. Okay. To build this Klein is 2 steps. We're going to build the Klein that does this without thinking about it as a transformation. To build it, what we first do is create, so make the circle through Z naught star and 0. And I'm going to call that C1. I'm going to do it red up here so that we have it. So in other words, I'm going to make this circle right here. That's C1. I feel, okay, I'm starting now to feel safe. I know what's happening now. I know what I want to say anyway. All right, so that intersects this guy at 2 points. Let's just pick one of them. P. 2. Mark a point of intersection P between C1 and the unit circle. Doesn't matter which of these 2 you pick. Then get out a big ass compass. I was gonna make one. I did not have time or energy last night, but I wanted to go into my wood shop and build a compass that would allow me to make nice circles in here. I bet Dr. Patnot's got one, but I don't. So the next step, and almost the last step, is to now make a circle with center Z naught star and that passes through P. So you can see why I kind of need, yuck. That should have gone through the other. That is clearly not a circle. And it should have gone through this guy, so I'm going to tweak him. No, it's definitely not a circle. So step 3 is create a circle, center Z naught star of radius that passes through that P. I guess that's a good way to say it. So step 3 is create a circle, and this is the circle we want. Now I'll prove that to you. Create a circle C with center Z naught star and passing through P. That's the circle we're looking for. So here's my claim that when we flip Z naught about this circle, when we invert that around this circle, it goes to 0. That was the construction. We're going to prove that that happened. So there's 2 things to notice here. The first is that if I create the triangle, let's actually put up what we're going to show so that we can kind of see it more. We show that inverting Z naught about C sends it to 0. And that'll have half of what we want, or a third of what we want. In the process, what would inversion around this green circle do to its center? So if I invert around this green circle, what happens to its center? Goes where? Infinity. So if I invert around big greenie, this is definitely going to infinity, and we'll have another part of what we want. Note that inversion around C sends its center, Z naught star, to infinity. So then we have that part. And all I have to do now is show that we're going to get to 0. And then we've got one more reflection to do, and that's going to be the one that's going to move 1 to, that's going to move some point here to 1. So we'll worry about that in a minute. Let me stop. Tell me if you're following. Definitely not getting past this today. They got like 15 minutes left. This is about it. We're not doing more. Okay. So here's what we have to notice. This red circle, if I make this triangle 0, hold on, don't do it yet. I gotta make sure I get it right. 0, P, that line, make that line look tangent to your big circle, because it is. It just doesn't look like it here. And then the line from the center to P. So if I make that triangle is a right triangle. Now I gotta think, why do I know that? Oh, okay, I do know that. Why do we know that? Why do I know? We see that triangle 0, P, Z naught star is a right triangle. Why? You tell me. Lou, what you got?
Is it because the line from 0 to P is tangent to the green circle, and then the line from Z naught star to P is the radius and is then perpendicular to a parallel line?
Actually, it's not. So I drew this in here. That's what we're trying to prove. So we can't use that tangency because we're going to get that tangency from this more basic result. So think about the red circle. Let me give you a hint. It all has to do with the red circle and how the triangle sits in the red circle. And we did this a long time ago. If I make a circle, any circle, and I cut across the diameter, and I make a triangle inside of it, what do I know about that triangle? Well, I'll tell you, it's a right triangle, no matter how you do it. So if you take a triangle that's made inside the half of a circle, no matter how you do it, it's a right angle, and that can be proved. We're not going to prove it. Used it like ancient million years ago when we started talking about inversions. So we see that because it is inscribed in in half a circle with the diameter as one side. That's a fundamental geometry result that we're just going to assume. So now, Lou, now I get that right angle out of that. Because this side here, 0P, only touches the green circle at one point. Because of the way that I made the green circle, right? I made this green circle to pass right through that point. It pulls away from that line at that moment. So that means, thus, let's use a thus, I haven't used one of those in a while. Thus, angle Z naught P0, Z naught star P0 is a right angle. And big C, green C, is orthogonal to our unit circle. And so C is orthogonal to the unit circle, which we call S1 infinity. Oh my God. So if I invert around green circle, why does this go to 0? I'm going to give you a moment on that. So we know, so let's think about what we know. We know that big C, that's the greenie, is orthogonal to our unit circle. We know that Z naught star, when I invert around C, so let's see here. So inversion about C sends, we already got this one, Z naught star to infinity. Why does Z naught get sent to 0? And the answer's already been said earlier today. I gotta stay away from people. I think I got so sweaty in this whole thing. I don't think I smell good. Math club should be fun. Enjoy the salsa. Why is that? What does inversion around a Klein do to symmetric points? Is that, you got it?
Yeah. Is it because it keeps symmetry with the Z naught star?
Exactly. So Z naught star and Z naught are symmetric. So if I invert them symmetric with respect to this unit circle, if I invert this unit circle, if I invert C around this unit circle, then it sends Z naught to infinity, and it has to send Z naught to its symmetric partner. The partner of infinity is 0, because symmetric partners, symmetric points get sent. So we're using that fact that, Christian, you pulled up a little earlier. It's just kind of in a different layer right now. Gets sent to symmetric points. Thus, again, if Z naught star gets sent to infinity, Z naught must get sent to 0, because those are symmetric, because these are symmetric. Holy shit. Wow, okay. So we got 2 things done. This big first inversion is the thing that sends 2 of our points to the places we wanted to send them. We have one last thing to do, and I need a fresh pen for it. We need to find out who gets sent to 1. So, lastly, we have this note that any T, if T sends the disk onto the disk, it sends the boundary onto the boundary. And we could prove this. I'm not going to make you prove this. T sends S infinity 1 to S infinity 1. In other words, the unit circle just gets mapped to the unit circle, which kind of makes sense. If you're mapping the whole disk back onto the disk, the boundary gets mapped to the boundary. We can prove that. I think they might ask you to do it in one of the exercises, but I didn't assign that exercise. So, since 1 is on the boundary, right, let's here. So here's our disk, here's 0, here's 1. We've got this T already. We started building it through inversions, but we know that T itself maps all of this stuff onto this stuff. So it must map 1 onto some point over here. So since 1 is on the boundary, there, oops, sorry, I got this ass backwards. Sorry. I want to hit 1, sorry. So to hit 1, there's some point here that hits 1 on the boundary. we map it through T. So since 1 is on the boundary, there is some Z1 also on the boundary, such that T of Z1 equals 1. Thanks. Right. Cool. So when we did this stuff here, that Z1 that was on the boundary got moved. When I did this inversion in the big green circle, the point that will hit 1 gets moved. It doesn't get moved to 1. It gets moved somewhere else. Z1 star. So let's make a note of that. We're almost done. Hang in there. You got this. I don't have much room here. I guess I can get rid of that guy. A lot of that. When we inverted about green circle C, we sent, I'm going to summarize a little bit here. We sent Z0 to 0. We sent Z0 star to infinity. And that point, Z1, got sent somewhere else. We don't know where. Let's look at just the boundary. So this was our original, this was the original point. This will get sent to 1, but inversion around this wasn't the whole thing we were doing. So it got sent to some Z1 prime. Here's 1 here. So I want to get that to there while preserving what we've done. I don't want to change Z0 and Z0 star in any way. So what we're going to do is we're going to draw a line through 0, 1. We're going to draw a line through Z1 star. And our last operation, the very last thing we're going to do, is we're going to flip over the bisector of this angle here. So this is the bisector of angle Z1 prime 0, 1. And we're going to reflect over that. And if you just flip over that bisector, it takes Z1 prime to 1, which sends, so flip over the bisector of that angle, which sends Z1 prime to 1. And we're done. So the T that we're looking for, now think of T, this is it, as the subsequent flips over C, and then 2 over that bisector. And what we'll have is our transformation. And this is 2 reflections. These 2 reflections achieve I before E, I don't know, achieve T of Z0 goes to 0, T of Z1 goes to 1, and T of Z0 star goes to infinity. Oh my God. So, there's a subtle point here, but I'm going to let this sit in your brain over the night, over the weekend. I want to come back to this just on Monday and just quickly recap what happened, but also explain why didn't I move? And actually, maybe you can answer this question. Here, I have a question for you. Why didn't we change what happened to Z0 and Z0 star? Why didn't anything change? Think about that, and I'll ask somebody when we we get here. So yeah, you got it. So notice, all right, we did all that work. We did all this fancy shit. Send this guy to 0, send this guy to infinity. And then I come in and then I flip this whole thing. Why are the other 2 points okay? That's the question. Read through the proof. They actually tell you in the proof. So the secret, the answer is just hidden in the proof in the book. But you might want to try to think it through on your own. And we will pick up there on Monday. Please come back. Please come back. 3 weeks left.